I welcome everybody in the room. This is the first time we are doing it in hybrid format. We expected a little bit a larger audience to be present physically, actually. But obviously, I welcome also everybody via Zoom. And it's a great pleasure to introduce Malcom McLeod to you, who will be giving this lecture on research improvement strategies to reduce waste, increase value, and transform the experience of being a researcher. So there is some expectation behind that title, at least on my side, to hear quite different aspects around the topic of research waste. Malcom is a neurologist by training and a professor of neurology and translational neurosciences at the University of Edinburgh. I stumbled across, when I looked a little bit more deeply into the topic of reproducibility, and especially in the UK. And Malcom is a steering group or steering committee member of the UK Reproducibility Network. But he started, which was built, I think, I don't know, he will probably tell. But he started much earlier to think a little bit about the aspects of research waste, quality, reproducibility, already were related to his work in preclinical animal studies, where he worked quite a bit, also on the topic of reporting guidelines, which should be very familiar to a lot of people in the audience, because it's also an important topic in Bern. But he did quite a bit of work also on looking into evidence for interventions to improve the quality of research or to reduce research waste. At least that's my understanding, and I hope we will hear a little bit about that in the talk. For the formalities, I ask you to mute as normal. Keep your questions, because this is the first time we will do it in hybrid mode. We are not sure whether I will be able to pick up your raised hands at the end when we have the discussion. So we will see how that works out, because we don't see the chat here in this room so easily. So we will have the talk by Malcom. Please keep your questions until the very end, and then we will open up the discussions. Malcom, the stage is yours.
Well, thank you very much, and good afternoon, everyone. I'm going to try and take you through really what's been 20 years of growing frustration and experience in how we might improve research. And I hope it's interesting, if somewhat worrying. And I should say that, as well as a recording of this talk being available, my slides are available in the Open Science Framework with that link there, if anyone wants to take them, reuse them, take them to bits, put them back together again. So I've got no financial conflicts of interest, but I think my background does give me some conflicts, or at least a perspective against which I've learned what I've learned. I did an in vitro PhD and an in vivo postdoc almost 30 years ago now. I've been doing systematic reviews and meta-analysis predominantly of animal studies for 20 years, been involved in various clinical trials over that time also. Been a clinical neurologist since 2005. For 8 years till this year, I've been a drug regulator with the UK Commission for Human Medicines, which approves new drugs coming to the UK market. Was in authorship in the Lancet series of Waste and Research almost 10 years ago. For the last 3 years, I've been trying to lead us in Edinburgh to improvements in research and researcher integrity. And The only bit that's potentially a conflict is that I'm the chairman and coordinator of the guarantors of the Ensuring Quality in Preclinical Data Network, since it was formed last year as a follow-on to an IMI project. And my life has really been about trying to translate findings from one domain, if you like, from one language to another. And this is a road sign from Wales. It could equally be a road sign in Scotland, because similarly we have a fetish in trying to resuscitate dead languages. And it says no entry for heavy goods vehicles, residential site only. And underneath it says the same thing in Welsh. Although actually it doesn't, because if you translate what it says in Welsh, it says, I am not in the office at the moment, send any work to be translated. So this, like this translational road signist hasn't understood their technique, their methodology. They've simply sent their data off to be analysed. They've had their data sent back and they've believed it without doing any due diligence on the process involved. And really, I could stop there in large part because I think that's at the heart of many of our problems. Here's an example of a study using functional magnetic resonance imaging scanning. This is a technique which uses something called the blood oxygen level dependent signal. And it rests on the basis that if part of your brain is metabolically active, then the venous drainage from that part of the brain has got products of metabolism which cause a venodilatation, which one can detect in a scan. And so you can see which part of the brain is turned on when you do something. These machines are very temperamental and they need to be tended and set up and trimmed every week to make sure they're working just perfectly. And this group in Boston had a competition to see who could bring in the most unusual piece of organic material to put in the bore of the scanner to set it up. And the prize was free beer at the work barbecue that summer. So it was a competition worth winning. And one week it was Craig Bennett's turn, and he was on his way to work when he realized it was his week and he didn't have anything to put on the scanner. But fortunately, his route to work took him past the Boston Fish Market. So he said, no one's ever had a fish in the scanner before. It might make it smell for a day or two, but I'll win the prize, and that's what's important. So he got the fish in and they twiddled the knobs and set it all up, and they were all good to go. But then their healthy human volunteer didn't show. And his genius was to do the experiment on the salmon. So one mature Atlantic salmon participated in the fMRI study. It was 18 inches long, weighed 3.8 pounds, and they didn't know if it was alive or dead, but given that it was dead, they didn't know if it was male or female rather, but given that it was dead, they didn't think that this was important. And the task administered to the salmon involved completing an open-ended mentalizing task. So the salmon was shown a series of photographs of human subjects with a specified emotional valence. They were happy or sad or perplexed. And the salmon was asked to determine which emotion the human subject was experiencing at the time. And several active voxels were observed within the salmon brain cavity with a cluster level of significance of less than 1 in 1,000. So as they conclude, either we've stumbled onto a rather amazing discovery in terms of post-mortem ichthyological cognition, that's to say that dead salmon can think, or there's something wrong with that uncorrected statistical approach when there are literally tens of thousands of different ways in which these information can be processed. And of course, the latter is true, and for which they won the Ig Nobel Prize for Neuroscience in 2012, and rightly so. But these are radiologists. I don't know if there's any radiologists in the audience, but in the UK, they don't necessarily have a reputation for being in the top half of the class at medical school. Some of my best friends are radiologists. But what about proper bench scientists? We know what's going on, don't we? We know what truth is. So this is an experiment from the Walter Reed Institute, Bethesda, part of the NIH campus, looking at the neuroprotective effects of low-dose glutamate and homeopathic arnica montana in a rat model of middle cerebral artery occlusion. So essentially you take a rat, you occlude one middle cerebral artery, and then you either give the rat treatment or control, and you come back at 72 hours and measure the volume of brain that's been killed off. And you can see that half-dose low-dose glutamate is quite protective, and full-dose low-dose glutamate improves infarct volume by about 40%, industry standard neuroprotection. But when I tell you that half-dose low-dose is 10 to the minus 120 molar and full-dose is 10 to the minus 60 molar, then those of you who remember Avogadro's constant will realize that there isn't any glutamate in either of these columns, and what we're seeing must all be biased. Of course, the homeopath, or either that or homeopathy works, but the homeopaths would have us believe that 10 to the minus 120 molar being more dilute would be in fact the more powerful treatment. So these findings are not consistent with the tenets and belief either of conventional medicine or of homeopathic medicine, and must simply be wrong. And we first came to this many years ago when we were interested in the development of drugs for stroke, and specifically if there were drugs which were already known to be safe, which we could repurpose and give to stroke patients in the back of an ambulance, so we could shorten the interval between stroke onset and treatment, which is held to be one of the major barriers in developing stroke therapeutics. We found over 1,000 compounds that had been tested in the lab, of which 600 had been tested in animal models of stroke, of which remarkably almost 400 had at least one report that had improved outcome in those animals of stroke. And we then went on to look at whether they'd been tested in clinical trial, and 97 of them had been tested in clinical trials, and of those, one clot-busting treatment with tissue plasminogen activator was effective in clinical trials, and 96 were ineffective. And in fact, TPA was tested in stroke not because it works in animal models of stroke, although it does, and we've got a systematic review that shows that, but rather because it works in a cognate human condition, heart attacks, myocardial ischemia, caused by critical occlusion of an important vascular supply. And against that, we've got 3 treatments which do work in stroke. We've got stroke unit care, decompressive hemicraniectomy, and aspirin, none of which were developed for stroke on the basis of animal experiments. So depending on how generous you're feeling, this has got an attrition rate of either 100% or 99.7%, but either way, it doesn't represent a good return on the millions of euros which have been invested in stroke research over the last 20, 30, 40 years. So something's wrong and we need to change. And some of you might remember the old joke, how many psychiatrists does it take to change a light bulb? The answer being only one, but the light bulb has to really want to change. And one could repurpose this joke to say, how many crises does it take to change research practice? And the answer would be only one, but research really wants to have to change. So if we think about the reasons why a research finding might not be reproducible, why I might do an experiment in Edinburgh and you try and reproduce that experiment in Bern and not get the same result, I think there are several reasons. Some of them entirely reasonable and some of them less reasonable. So firstly, the valid research claim might have been made on the data which were observed, but the statistical test returned a type 1 or a false positive error. We know that that will happen 5% of the time when the null hypothesis is correct. And so maybe it was that. Maybe the research claim was valid under the particular circumstances under which it was tested, but not observed under the circumstances in which replication was attempted. And importantly, those different circumstances may be known, different species, different strain, different dose of drug, or may be subtle, or may be completely latent, and their impact on the observed phenomena may or may not be important in understanding the question at hand. Thirdly, the observations might have been due to suboptimal study designs, which, for instance, would allow the emergence of experimental bias or selective data presentation or whatever, and you might collectively consider these to be questionable research practices. They don't represent researcher evil wrongdoing, but they do diminish the credibility, the provenance of the research findings. Of course, if a researcher continues to engage in such wonky study designs, having been told that they're wrong, then that does stray into category 4, which is researcher integrity, the research claim made following deliberate researcher malfeasance, such as falsification or fabrication. But the thing that's most interesting to me is this category 3, the sort of things that we do that might represent shortcuts or might represent a slightly easier way of doing things, or might simply represent the way that we were taught to do research that give opportunities for bias to intrude. So I think research quality can be considered, and academic excellence can be considered as a 3-legged stool. One leg is the inspiration. It's sitting in the garden and an apple falling on your head and thinking, oh, that must be gravity. Or lying in a bath and seeing the water level increase and say, oh, that must be volume displacement. And you can't really hire people or fire people on the basis of that inspiration. It either happens or it doesn't. But project design, the ability to take those ideas, those concepts, those insights into how the world might be, and say, how can I design an experiment at low risk of bias, with appropriate data management, with appropriate ethical reflection on what I'm doing and why, and what the risks are to participants and more generally are mapped against the potential benefits. How do I design the experiment? How do I pre-register it to hold my own feet to the fire? And then in the execution, with transparent reporting and appropriate analysis, making appropriate and well-evidenced evidentiary claims rather than overstating things, making your materials available, disseminating your work in a way that research users can use and reuse your data to extract maximum value. So weak studies then are ones which have wonky experimental designs. They don't randomize, they don't blind. They're underpowered. They hypothesize after results are known. You know, traditionally we establish a hypothesis and then do an experiment to test it, but sometimes we stray, having collected the data, into misremembering what our hypothesis was, or sometimes even to making up a completely new hypothesis. Flexibility in data analysis, we touched on that with MRI. Dressing up exploratory research as if we were testing hypotheses. You know, we start to look at one thing and end up looking at another. And single center studies rather than findings which have been replicated across a number of studies. So for instance, this exploratory research question is best exemplified for me in a drug that came up for regulatory consideration, which was against one of the metabolic myopathies, where the manufacturer had sponsored a small phase 2 study targeted to test safety, had also measured some efficacy outcomes, and one of those efficacy outcomes had very helpfully dropped below P of 0.05, and rather doing what they should have done, which was to go on to do another study, which was specifically directed as testing the hypothesis that this improved outcome, they rushed for regulatory approval and were quite rightly knocked back from regulatory approval. So think about where these sit in a research life cycle, and this is from Marcus Munafo and colleagues in Nature Human Behavior. When we generate and specify a hypothesis and design our studies, we might fail to control for bias, we might have low statistical power. When we conduct our study and collect our data, we might have poor quality control. We might p-hack by analyzing the data every which way and picking the result that gets us over under 0.05. Similarly, when we interpret results, similarly when we want to publish or to conduct our next experiment. I just want to go through a few of those things in a bit more detail as exemplars of where things can go wrong. So this is small group size and publication bias. This has been described as the winner's curse. These are real data from Hanna Vesterainen's PhD thesis, which was a systematic review meta-analysis of the effectiveness of candidate drugs in experimental allergic encephalomyelitis, the animal model, one of the preferred animal models for multiple sclerosis. And what you see is that the larger the groups, the smaller the efficacy. So small studies show really this is a 50% improvement in neurobehavioral score in experiments with between 1 and 4 animals, falling away to a 30% improvement with 10 or more animals. Difficult to see why that would be the case unless you believe in the winner's curse. And let me just show that to you. So imagine, this is simulations, imagine that we've got 1,000 studies of each kind. We've got a complete publication bias in that anything where the p-value is greater than 0.05 remains unpublished. And let's model a true effect size of 10 with a standard deviation of 10. What do we see? Well, first of all, this is in effect a bootstrap power calculation. If we've got 5 animals per group, only 30% of our studies get published. If we've got 20 animals per group, 86% of our studies get published. So this means that the 20 animals per group is powered at 86%. But then let's take those 30% of studies that were published and do a meta-analysis of their findings. This is what we see. And there's a couple of things to note here. The first is that the estimate of efficacy falls in almost exactly the same pattern as we observed in EAE, simply because of this publication bias. The second thing is that even when we've got studies which we would consider to be adequately powered, there's an absolute overstatement of efficacy, sorry, a relative overstatement of effectiveness here of about 1%, from 10% up to 11%. So even adequately powered studies overstate effect size. Now, p-values and their interpretation. So when I was young, I mistakenly believed that if p was less than 0.05, it meant there was a 5% chance the findings weren't true. But of course, it critically depends not only on what's happening in those studies where there is a genuinely underlying true null result, but also the proportion of studies where there's actually an underlying effect of the drug in question. So let's imagine that we're testing 250 drugs for stroke in an animal model, of which 200 are inert, but 50 improve outcome. And let's suppose, for the sake of our argument, that those stroke studies are powered at 20%, and we know that actually most stroke studies in animals are powered at less than 20%, and that we take a 5% error rate, a 5% false positive rate. So what we find is that of our 50 drugs that improve outcome, we detect only 10 of those. And of our 200 drugs which don't improve outcome, we falsely call 5% of those 10 studies as being positive. And what that means is that if we look at positive studies, there are 20 positive studies, of which half of them are false positive and half of them are truly positive. So you can infer something just from the p-value, and this is the kind of cartoon basis of the Ioannidis 2005 why most published research is false. And to get to the level, which is where we conventionally think what we think p of less than 0.05 actually means, we would need to be powered at 80%, and we would need to take a p threshold of 0.01 to then end up with a situation where only 2 out of 42 studies with positive results were falsely positive. And that means increasing the size of the study from about 10 mice per study to typically more than 75 mice per study. So you can see why this doesn't happen very often, but that's what one would have to do. And then finally about heterogeneity, because in animal studies, we're trying to model the human condition, and in our human clinical trials and in my clinic, humans come in all sorts of shapes and sizes and ethnic backgrounds and comorbidities and the like. And yet when we do our animal studies to try and model this, we tend to do our animal studies with a very homogeneous range of animals in each individual study, different between studies, which is perhaps another reason why animal studies find it so difficult to agree with each other. And let me show you how this is relevant. So this is a series of systematic review meta-analyses of stroke drugs. Each dot is the point estimate for a stroke drug, with this vertical line here being the line of no effect. So across here to the left of your screen, the drugs improve outcome, and to the right of the screen, they make things worse. So most drugs improve outcome. Up and down the x-axis here, though, is the variation between experiments and how good the drug is. So for the two most extensively tested interventions, we've got hypothermia here, which is about twice as effective as thrombolytics. But you can see that the variation between studies in the effectiveness of hypothermia is quite large. Thrombolytics have been tested across a broad range of circumstances, over 300 experiments. And yet the variation between those experiments is fairly narrow, which gives us, I think, greater confidence that the effect of thrombolytics is real, and maybe one of the explanations for why thrombolysis has made it into clinical practice, and hypothermia, despite my attempts and those of others, has not passed the hurdle of positive clinical trials. So if we're going to set about improving things, I think we do need to recognize that researchers are different one to another. And I like to think that there's a kind of skewed normal distribution, and that more of us are above average than are below average, if you see what I mean. But this curve is then defined by things like falsification and fabrication and plagiarism at the extreme end, and then hypothesizing after results are known, and then the questionable research practices and risks of bias, and then better research characterized by commitments to open science and the like, and to pre-registration and to the registered reports format. And so what conventionally we do is to try and identify the people at the lowest end of this distribution, usually to shout at them in meetings and then to fire them from the institution, packing their belongings in a cardboard box and marching them from the building, pausing only to remove their library card and telling them never to darken our door. Again, of course, at the same time, writing them a glowing reference for employment in a different institution. But I'm not sure that's the right approach. So if we can imagine, again, this distribution, there are two options. One is to try and get rid of the most egregious practices and get these people removed from our community. But actually, we would have more effect on the quality of research as it is done if everyone who did research got just a little bit better at doing their research. So it's a bit like managing blood pressure in the population or managing salt intake in the population. Making a small difference to a large number of people has a greater effect on the general health of the system than trying to get rid of the people with the most extreme risks, the most extreme behaviors or practices. And so then that brings us on to a system where instead of research accountability, where we hold people individually responsible, we have this perfection myth. We consider solo practitioners, we really ignore peer review, whether local or national, and when we find shortcomings, we see them as things which must be punished. Research improvement should focus, and does focus rather, on systems rather than individuals, recognizing fallibility, endorsing the importance of teamwork, valuing local and community review of what are the important things to measure and the standards to measure people against, and finding shortcomings as opportunities for learning rather than for punishment. But then that gets us to the question of, well, that sounds fine, but what are we going to improve and how do we know what will improve and what will work, which kind of then brings us back, or brings me back to a bit of my kind of core business, my skill set, in that we've got an intervention which we think might lead to an improvement, and we've got to work out how we can test whether that might or might not be the case. And I like to think about this in terms of what I call the research improvement cube, which across 3 dimensions tries to place these interventions in a framework of the benefit of from the intervention, the cost of the intervention, not just the financial cost, and the certainty that we have in these estimates. So you can imagine if we've got an intervention down here where we've got high certainty that it's of high cost and of low benefit, then clearly we're not going to implement that at all. And if we've got an intervention here, which we've got low certainty, but it's low cost and high benefit, then this is something that we might just want to implement and say, well, let's just go ahead and do it. Let's just go ahead and do it and see if it works. And of course, if you had an intervention where you had low certainty, the costs were high, the benefits might be high, then that's the sort of situation in which you might think about a randomized controlled trial of intervention. I'll show you an example of that later on. So we've just had this week the announcement of what we now call the Research Excellence Framework in the UK, a supreme piece of nominative determinism. In 2008, it was called the Research Assessment Exercise, and it thought everything was brilliant, really. So we looked at the animal research outputs from the 5 institutions which led in those units of assessment in RE 2008, and we collected up their animal research outputs for the years 2009, 2010. We got over 1,000 publications, and for each of those, we asked the question, did it randomize if randomization would have been appropriate? Did it blind? Did it report inclusion, exclusion criteria? Did it report a power calculation? These institutions are color-coded to protect my future employment prospects. I'm delighted to say that Edinburgh University was one of these leading 5 UK universities. There's a lovely Scottish blue colour here, isn't it? But you can see randomization overall in about 1 in 6 papers, blinding in fewer than 1 in 5, inclusion exclusion in about 10%, power calculations reported in about, or any justification of sample size, in fact, in about 1 in 50 of those publications. Only 1 paper out of over 1,000 did all 4 of these things, reported all 4 of these things, and 68% of publications from leading institutions doing animal research in one of the leading biomedical research countries in the world, 68% did none. So this seems to me to be a potential focus for improvement. So how might one actually go about that? Well, based on reporting guidelines or research on research or expert opinion or what research users say they want. We get the community to assert what constitutes best practice, and then we measure performance against that standard. And then through training and incentives and interventions, guided perhaps by improvement specialists that might just have foundational skills or field-specific skills, or might be generic improvement experts, and then measure performance again and review what happened, celebrate our successes, embed what worked into our standard operating procedures, raise our ambitions, and go round this cycle again and again and again. So it's critically important, I think, and we've been developing and leading some of this work in Edinburgh, it's critically important that topics for improvement and the criteria against which they're judged are developed with and by the research community. Asking the questions, what makes for good research practice in my field? What do I try to do or see other people do that I think, well, that represents good research practice? And what do I do or see other people do that I think, well, that's a bit shonky, I'm not sure about that. What are the barriers to us doing better research? And can we categorize into the things that we can change, the things that we can help others to change, and the things that we'll never change that we just have to set to one side? And what changes could we make today? And how could we know if they'd worked? And the focus of that could be at several levels within the organization. So it could be in an individual lab. It turns out in retrospect, I did a research improvement project as a PhD student, trying to make sure that the CO2 levels in my tissue culture incubator were constant and at 5% rather than ranging from 2% to 10%, which is how it started. So it can happen at several levels within the organization. And if you want details of how that co-creation might work, we've got a good research practice week coming up in Edinburgh that goes into some of those details. But some key elements from research improvement theory, and these slides are borrowed from Jill Curry, who's been leading this work with us. There must be an organizational commitment to quality. It's not enough for researchers to be committed, the organization has to be committed. We need to seek to fix systems, not people, to foster teamwork and group problem solving rather than laying it on individuals, to base our improvement decisions on data, not people sitting around a desk saying, yeah, well, that seemed to work, let's do some more of that, or that didn't work. To see this as being a series of cycles of continuous improvement. We're not trying to change the world tomorrow. We're trying to be 0.5% better tomorrow than we are today. And that will all add up. And there are no quick fixes. We need to do this slowly and carefully. So what are we trying to accomplish to establish our aim? How will we know that change is an improvement to establish what we're going to measure? What change can we make that will result in an improvement? And then so we plan and we do and we study and we act, and then we embed things into standard practice, or we continue doing what we were doing. But deciding on the scale of what you want is difficult. And this comes back to my question about whether you need an RCT or whether you can just go ahead. So if you've got no commitment from the institution with a large cost of failure and a low degree of belief that the change will lead to improvement, then you should start with a very small scale test and not do very much. But if you've got a high degree of belief that the change will lead to improvement, cost of failure small, strong institutional commitment, you can implement with audit. And I'll show you later on some of how that audit might work. So most researchers are highly motivated to improve the design, conduct, analysis, and reporting of the research. Many will already be involved in efforts that they might not consider, but one could consider to be research improvement activities. But there's few resources to support this within the rubric, within the infrastructure of institutions. So differences between other improvement settings like healthcare or whatever include the unique structures of academic institutions, our differing strategic objectives, quite a little bit of difficulty, I think, in defining the customer, and also the different nature of our product. You know, is it a paper? Is it a data set? Is it a new treatment guideline for X or Y or Z? So we've talked about systems-based solutions, and as an example of that, and I would just point you to this as a resource, we developed as part of an Innovative Medicines Initiative program, including Hanno Verbal, who I think is based with you. It was called the European Quality and Preclinical Data Quality System when it was supported by IMI. We've now gone transatlantic as well, so we're the ensuring quality and preclinical data. And we're about to launch within the next few weeks a self-assessment tool. So as well as having a formal assessment process which involves external accreditation, we'll have a self-assessment tool that will allow institutions to reflect on what they've got and to see if they might improve it, done through the vehicle of the guarantors of Acquit. So the first approach might be to implement with observation. So here's an example from a while ago now. Story Landis and colleagues, led by Shai Silberberg, really published this in Nature in 2012, calling on transparent reporting to optimize the predictive value of preclinical research, identifying 4 things that they thought every paper should do. And with Veronique Kiermer, who was then at Nature, we developed a change in Nature publication, Nature guidelines to authors, which were heavily policed by the editorial team. And we did a study funded by the Arnold Foundation about whether that made a difference. So we took papers in Nature and in Nature type journals in blue here, before the change and after the change. And for each paper, we used PubMed related citations to identify a similar paper in a non-NPG competitor, again, looking at it by quarter. And you can see that for each, there is apart from perhaps power calculations, even in the non-Nature journals, there's a little bit of improvement in this interrupted time series analysis, but there's much more of an improvement in the Nature journals. Unfortunately, this took a lot of editorial input at Nature. It was taking up a lot of their time. And that was one of the reasons for the genesis of the MDAR framework that we published last year in PNAS, which is a kind of stripped down version, which might be easier to implement. Because it had been said around about the same time, you just need to have guidelines and enforce the guidelines. There's a set of guidelines for animal research called the ARRIVE guidelines, endorsed by over 1,000 journals. But then someone came along and made the rather unhelpful observation that there was no difference between the reporting quality in journals that endorsed the guidelines and those which did not, and it didn't seem to be changing very much, or at least not very quickly. And the response of those who'd authored the guidelines, not unreasonably, was journals just had to be better at enforcing compliance with the guidelines. We thought that was an interesting hypothesis. So we did a randomized controlled trial led by Emily Senna, where manuscripts submitted to PLOS One, which described animal research, were randomized to normal handling, which was simply an email saying, "We like ARRIVE, please send us your completed ARRIVE checklist," but just sending the manuscript on, compared with enhanced handling, which was, "Your manuscript's going to sit on my desk until I get your ARRIVE checklist, so hurry up and do it." And we randomized, and then we tracked these through for the ones that made it through to publication, and then trained a crowd of reviewers to evaluate those publications against the ARRIVE guidelines, which at that time, even though there was only 20 items on it, had to be operationalized into over 100 checklist items. And we randomized over 1,600 papers, and almost 700 made it through to publication. The intervention seemed to have taken, that's to say, about 90% of the manuscripts in the intervention group had a completed checklist. About 3% of the manuscripts in the non-intervention group had a completed checklist. So did this make a difference? The answer is no, because not a single one of any of these publications was ARRIVE compliant, which just shows you that something that you think is going to work doesn't necessarily work, and shows you the importance, particularly if you're going to take up a lot of researcher time, the importance of having confidence that your intervention will actually deliver and that you're not just wasting everybody's time. And I think there's not nearly enough research on research into the effectiveness of these approaches. Here's some other things that we're doing, just to give you examples. This is based on the premise that delays to publication cause delay to benefit, particularly around animal research, and so reduce the harm-benefit position of animal research. So if my animal research is supposed to lead to development of a treatment, for instance, of ALS motor neuron disease, and it's the basis of a chain of 5 animal studies, each of which is delayed in peer review by 6 months, then that means I've delayed a treatment for motor neuron disease by 3 years, which you can just count the coffins for what that costs. So we looked at experiment request forms for animal research in 2014 in Edinburgh, and then essentially did Kaplan-Meiers of survival in the unpublished state. And you can see we've got the median interval from the experiment being approved to its submission for publication of about 756 days, and median delay to publication of almost 1,000 days. But if you then separate out the delay from submission to publication, the median delay is 234 days, 235 days, with an interquartile range that goes up to almost a year. And in this time here, these are zombie publications that people can't see, can't use, can't exploit. And to be clear, we took the data first, online availability. And so through the use of preprint servers, for instance, we can get this delay down to about 2 or 3 days rather than 235 days. And we're now working with our researchers to understand what they think about bioRxiv, what they see the barriers as being, what help they might need, etc., etc. Here's another one. This is a hat tip to Nick Riedel, until recently in the Charité, looking at the proportion of our publications in my own research group, our Centre for Clinical Brain Sciences stroke research group, the proportion of publications which are open access and what kind of open access publications they are over the years from 1990, or in the lower panel 1994, through to 2021. You can see there's a slight fall off in our number of publications. The top is the absolute number. That's due to retirement of people more productive and effective than I am. But our proportion of open access publications in 2021 was 82%. And we know that that's quite good, but we'd rather next year it was 85% or 90%, and we'd rather in 10 years' time it was 100%. And so this gives us a dashboard that allows us to monitor our performance on a key performance indicator like this, and to judge the effectiveness of interventions against that. So an improvement strategy then should identify an improvement need, identify or develop interventions which might help, locate those interventions in the research improvement cube so you know whether you need a trial or whether you can simply implement as part of an audit cycle. And then if you fix your problem, embed into standard practice, move on. And if not, try again. Different intervention, same intervention, differently delivered, same intervention delivered with greater enthusiasm, and so on and so on. I promised you something about transforming the experience of being a researcher. And I think this is absolutely critical. And I also think it is intimately entwined with issues of reproducibility and rigor and the pressures under which researchers find themselves. So I want to share with you some data from the University of Edinburgh Research Culture Survey, which I led in 2020, where we had around 1,500 respondents. About half of them were postgraduate students, half of them faculty or postdocs. We did a trial within us, and that represents about 1 in 8 of our researchers. We did a trial within a survey of different incentives. So we randomized people to different incentives. It showed that there was no effect, like just about every other trial I've ever been involved with, but that's helpful for us because we're doing another trial, so we know what we don't need to do. All the materials are available in the Open Science Framework with that link, and data stripped of demographics, so you can't do jigsaw identification, is available on Edinburgh DataShare. And we've analysed these. Most of the questions were Likert scales, 7-item Likert scales, and we've organised or analysed these using ordinal logistic regression as if it were a clinical trial to see whether aspects of demographics made a difference to the responses and the experience of our research culture. And so you see them here: academics or students or others, whether they're arts, humanities, social sciences, or science and engineering, or medicine, vet medicine, whether people have caring responsibilities, whether they've got self-reported disability, ethnicities, first generation to university, their gender, their sexuality. So there's just some things that I'd like to draw out. And in all of these, being on this side of the bar, being on the left side, reflects your experience. That's an odds ratio less than 1. Your experience being less good than the average of all respondents and the aggregate of all respondents. Out here on the right, you've got a better experience than most. My supervisor gives me freedom to explore my results. Well, arts, humanities, social science are the reference group here. CMVM, people feel less freedom. People with disability feel less freedom. males feel more freedom than females to explore their results. Leaders communicate clear expectations. So it's flipped here by colleges, but again, people with disability have a less good experience with research culture. Not so many differences down here. How important do you think it is that the institution promotes leading and supporting teams of diverse individuals? So we're all very woke up here in medicine. We believe that this is important, but look at this. But with an odds ratio of about 0.5, men think actually that's not that important. And LGBTIQ clearly think that this is more important than their straight colleagues. Let's look at some more. University could do more to ensure that research practice don't cut corners. Again, there's this signal with disability here. Comfortable reporting instances of compromised research strategy. Again, there's this. So and men feeling very comfortable here. I've received training on managing. So what was absolutely striking for me in all of this, and had been completely, I'd been relatively oblivious to previously, 12% of our respondents reported disability, either in either mental or physical of cause, and they were about evenly split. And they had collectively the worst experience of a research culture than any other demographic, be it by gender or race or whatever. Their experience was systematically worse. And that's really informed our thinking about what we do about research cultures. Here's some more. During your career, have you experienced bullying or harassment? A third have experienced bullying, harassment. A third have experienced discrimination. And not surprisingly, men less likely to have experienced discrimination, less likely to have experienced bullying or harassment. So this is really helpful, I think, going forward as we come to work out what we're going to do about it. So our research cultures are very differently experienced by different groups. Those who come from a privileged demographic, people like me, may be completely unaware of the experiences of and problems faced by others. The experience of those with self-reported disability are, I think, profoundly worrying. I've talked about the problem of bullying and harassment and discrimination. And we all have a responsibility to sustain a positive and enabling research culture in everything we do. And I just want to give you an example of how we've tried to do that. Emily's disappeared, but here she is here. There have this year been several Horizon Europe calls on reproducibility and on open and responsible research and innovation. And we were very keen with senior colleagues around Europe, we were very keen that we should walk the walk of giving voice to mid-career researchers. So with funding from the Royal Society in Edinburgh, we established a get-together meeting in Berlin in January, where we established 4 consortia, which had a novel mentored leadership model. That's to say, they were led by mid-career researchers, each of whom had a named senior researcher as their go-to mentor, so that when they applied, the panelists couldn't say, at least I hope they don't say, oh, you don't have enough experience for this, to give voice and opportunity to the next generation of meta-researchers. We established 4 consortia. 3 progressed to application. We'll find out what happened to them later in the year. One of them, I think entirely appropriately, didn't progress to application because what the call was looking for wasn't what we wanted and what the leader wanted to do. Essentially, it was one of the the European Science Cloud calls where they wanted some measures of reuse. So essentially, they were asking the question, can I reuse the data on EOSC? And we wanted also to ask the question, should I reuse the data on EOSC? Does EOSC and the repositories tell me enough about the provenance of the data for me to know whether I can trust it? And we couldn't find a way to work that into the application, and we decided better not to apply and waste people's time than apply with what we wanted to do that was wrong. And in another nod to openness and transparency, even though the panels have not yet met, the text of these application priorities, IRISE and Tier 2, are available in the Open Science Framework. So if we don't get funded, someone else can take our ideas and do the work. We think the work's good, we think it's valuable. We'd love to be in a position to do the work, but we're sure that other people could do it almost as well as us. And what's most important is that the work gets done. So I'd like to end by thanking the team. This is us on our last pre-pandemic get-together in Sweden. a number of colleagues there, including David Howells from Tasmania, who was involved in this from the very beginning. Emily Senna is here. This is Uli Dernagel from Berlin. This is me. I'm pleased to say that in lockdown, I've lost a substantial amount of girth, but you can see there was a lot of girth to lose. So thank you very much for your attention, and I'd be very happy to take any questions that you might have. Thank you.
Thank you very much, Malcolm. Thanks for the talk. Thanks for giving us some insights into what you are doing, especially also on the institutional level in Edinburgh. I ask first the audience, any questions, just unmute and raise questions. Raise hands or just unmute and speak up if you want to. If nobody asks questions, then
I see Nicola is turned her camera on and is waving at me. So either she's just really friendly, which is fine.
You want to say hello, Nicola, or you want to say something? We cannot hear you.
Can you?
Yeah, we can hear you now, yeah.
Now.
Okay, so thank you, Malcolm. As usual, absolutely brilliantly entertaining. And I've got lots and lots of questions, but just quickly, you know, you're talking to us as researchers mainly in human medicine, and your work on preclinical studies is really, really impressive. I also sit on a panel in a graduate school which has lots of preclinical scientists in it. What's the balance of talks that you do for people in human medicine versus preclinical? And do you think you get through to the preclinical researchers? Because my impression from your sample size slides is that, you know, we're still justifying, you know, 3 to 4 mice per experiment.
Yeah, I think there are particular constraints in preclinical experiments. I think the main problem with preclinical experiments is that people mistake exploratory work for hypothesis testing work. And they do work as exploratory, and then they get a p-value and they think, oh, that's great, we can publish that. That means it's now hypothesis testing. And that's I think that's to misunderstand what they're doing. And there's two approaches to that, or there's two ways of dealing with that. One is for me to do experiments which are big enough. Or the second, and I quite like this idea, and there's a bit of this has happened, which is to have consortia of animal researchers who agree to test each other's hypothesis. So I get to the stage where I've done the exploratoriness, and I think, well, this is good to go. And then I get my 5 mates around the world to do the same thing. And that then gets the numbers, up sufficiently. I don't think that clinical research is immune from these problems. I think clinical trials have come quite a long way, but we still know that there's lots of non-reporting of results. There's lots of selective outcome reporting. There's lots of hypothesis switching. One of our improvement projects, which I didn't show you because it was really pretty informal and just involved me, was trying to get our UDRAC CT completion report up, and it started off at about 53% and we got it up to 90%, but that was just by me annoying people until they did it. And I think that sort of thing's important. I worry a bit about observational research in that I think there are many, many more opportunities to collect loads of data and then to focus in on the stuff that looks interesting. And you know, observational epidemiology, if you don't have adequate pre-specification of what it is that you're after and what you're going to look at, I think is a bit wonky and a bit of a minefield. And as to changing behaviors, well, it's difficult to get anyone to change their behavior. But I've never met a researcher who wouldn't like the research to be better. What you need to do is to walk in their shoes and walk with them to help them make little changes. And then some of those individuals become the most powerful advocates for change in their own community. But I think this doesn't help.
Okay, thanks very much. I'll let someone else ask a question.
I have a question because you mentioned this, but you didn't touch upon that very deeply. This is about auditing, or do you see a role of? I mean, we have peer review systems, so especially in the basic science, I think, in the preclinical, which might also explain a little bit the publication delay because people go back to the lab. But my experience is, as opposed to clinical research where we have independent auditing in how things are actually conducted, this is rarely, if ever, done. Do you see a role in this, or is this basically individually focusing and blaming individuals, or pursuing a system of blaming individuals?
Well, I don't think it works. So the doing stuff to OECD GLP guidelines means that you've got a paper trail of what you did. But if you did the wrong thing, OECD GLP doesn't say anything about randomization or blinding, for instance. And ICH, whatever, is also mute on a number of things and completely overplays the importance of other things in terms of clinical trial design. There was a general practitioner in the north of England many years ago called Harold Shipman, of whom some of you may have heard, who was sent to prison for the rest of his life for murdering several of his patients. And one of my colleagues from medical school was an academic GP on his patch, and he said Shipman did a lot of recruitment to their studies, and he had the cleanest data records for his patients. There was not a data query on any of it because he. So I don't think that audit works. But I think audit is important, and in a clinical context, often we make this distinction between audit for accountability and audit for improvement. An audit for accountability is an external process, and audit for improvement is an internal process. And I think that if the audit process is owned by, so if I go into a lab tomorrow and they say we're worried about the CO2 in our incubator, or we're worried about our retention rate in our clinical trials, and I say, well, maybe you could, and this is data which are held within the group, and that's a very different thing from me coming along saying, now for all of our my response to this is, for all of our trials, we're gonna audit you on your retention rate, and we're gonna look at the top 10% and the bottom 10% and punish you. And that brings me on to the idea of research evaluations thinking about. So now conventionally our research evaluation systems are based on quality of our research outputs. So we produce research artifacts, and then whomever it is says, yes, this is a good paper, no, that's a bad paper, or yes, this paper has changed practice and therefore it's good. And I'm interested in how we might add to that by looking at quality by design. So for some of our pharmacologicals, the chemical synthetic process cannot be adequately defined. So for the heparinoids, for instance, it's very difficult to define how you manufacture a heparin chemically from stage to stage to stage. So you can't get good manufacturing process control there. What you can do is have quality by design, in that they say at each stage, we look at what we've got, we make sure it's within the tolerance limits, and then we pass it on to the next stage. And I'd like to see a recognition of the importance of quality by design in our research production process. So as an institution, we know that our research is good, not just because we've looked at the last 100 papers we published and they were good, but because at every stage of the process, we can see we're doing the right thing. And then even if our paper doesn't get cited, even if our work doesn't get published, we can be confident it meets the standards that we are most interested in.
Okay. Interesting. Okay. Other questions from the audience? One other final question then, and that's, you mentioned that institutional support is absolutely critical and important. It doesn't work without institutional support. Is it possible still for institutes, research groups themselves to do something, even though they are in a larger system embedded?
Yes, but it's more difficult and it's more challenging. It's less sustainable because it relies on individuals who might move on. And it means that the institution loses opportunities to generalize that learning to other parts of the institution. So it's possible, but it's not desirable. One of the things that we did in the UK when we set up the reproducibility network, so we've got local network leads, we've got institutions that can join, and we've got stakeholders. I know that you've got a Swiss reproducibility network. In ours, a criteria for institutional membership is that they have a senior academic who they fund for at least 1 day a week, who isn't in the line of research management, but has got access to that line of research management and, if you like, holds the institution's feet to the fire in doing the right thing around X or Y or Z. And so I think that's a good model, because now it means that with 20 odd institutional members in the UK, we've got 20 days a week for research improvement, if you like, just through that simple measure. I think that given the size of most institutions, the cost of a day a week of someone's time is trivially small compared with the amount of, you know, Paul Glasgow and Ian saying that 50% of research is wasted. Well, how much does UBERN spend on research? You know, how many millions of Swiss, whatever you have, euros, francs, cents, dollars, truths. How many millions of
we have everything in Switzerland.
Are spent by UBERN, and you know, what percentage of that would be too much to be spending on making it a bit better? And 1%, I'm sure, would go an incredibly long way.
Okay, thank you very much, Malcolm. Thank you for this talk. I think it is very important. Even though smaller groups might not be able to do something sustainable, but everybody is aware, and I believe in some grassroots activities that can help to change the institution at some point, I hope. Thank you very much. I hope we will see all the other audiences in the next lecture, which will be happening at the second half of June, again in hybrid format. Thanks, Malcolm.
Lovely, our pleasure. Thank you all very much for coming along.